Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Chuck has a long career in doing a lot of novel hardware capabilities. His research interests at Microsoft today mirror some of the things he's done over the course of his career with a specific focus on advanced networking capabilities. Notably, Chuck was also the person who drove the hardware architecture of the first PC tablets that we provided Windows support for. So he's been involved in a lot of the leading edge stuff. And notably, Chuck also last year was the Turing Award winner. So you can think of the Turing Award as the Nobel Prize of computing. We actually have two. Butler Lamson also is a Turing Award winner. So Chuck is going to give the talk this morning with his thoughts that he presented alongside the Turing Award. Chuck? Thank you.
Thank you, Craig.
Good luck.
We actually have 3 Turing Award winners. Tony. Okay, today I'll tell you about some things that I've been thinking about for several years. When I was notified that I won this award, I carefully read over all the previous lectures that Turing laureates have been given, and I noticed they fell into two broad categories. One is a sort of a career recapitulation, where you say all the things you've done throughout your career, and another is sort of grand challenges for the future. And I thought, well, I'm not very good at either of those things, so I'll try something else. What I will do is I will pick a thesis that I believe in, and I will defend it, and do that with some examples. And so here is the thesis. The fundamental thesis is that computer architecture has hit a wall. It's actually hit a couple of walls. There's the power wall, there's the memory wall, and possibly one of the biggest ones that people don't actually talk about very much is the complexity wall. And these walls are going to change the way we build systems. We're going to have to build them in new ways, and those new ways will require new ways of programming them. And the thesis is that in designing these future systems, we might examine some of the decisions that we made in the past about things that in computing we consider axiomatic today, and ask the question, are they really still a good idea in the 21st century? All of them were extremely good ideas when they were thought up, all of my examples. But it's less clear today. So I'll give some examples that I thought up. If you could choose them, you'd probably choose different ones. And we'll see how that goes. So here's a slide that I used to illuminate 40 years of progress in computing. This is the 1972 Alto, which was the computer on which Rick Rashid wrote his first video game. Programmed at the microcode level, and it was quite nice. A Star Trek game, as you might imagine. The clock rate of the Alto was 6 megahertz. The clock rate of my home PC today is 1,900 times faster. Memory size was 128 kilobytes. You cannot buy 128 kilobytes of memory anymore. It's too small. Today, my home computer is 6 gigabytes, a factor of 48,000. 1,900 in clock rate, 48,000 in memory capacity. But look at the memory access time. It's only a factor of 17. What's going on? That's the memory wall. The display pixels are 150x. That's pretty good. It doesn't need to be too much better because I can't see those pixels anyway. They're closer together to the resolution of my eyeball. Yours too, even if you're young. The network is 300 times faster. Maybe a bit better at higher levels of the network, but in my home it's 1 gigabit. Disk capacity is the interesting number. 280,000 times better. Where do those kinds of things come from? Well, they all come from the exponential drivers for computing. And here are the 3 major ones. Rotating magnetic storage is, of course, that factor of 280K. And today, I'm not worried about the storage. We can store every bit of every piece of information we received through an entire lifetime on a few disks. And of course, my colleague Gordon Bell is trying to do just this. The other thing that people sometimes forget is glass fibers. There's been tremendous progress in the ability of materials people to make clear glass and send a large amount of data through it. Today, no point, 2 points on Earth are more than about 70 milliseconds apart. Unfortunately, this is not for the internet. This is for the telephone network. And I'll give you a thought experiment to explain why I believe this is actually true. International long-distance calls work. And if the latency were much longer than that, they wouldn't. The conversations would stutter, and they don't. Now, they might stutter if it goes over the cell phone network, which has quite a bit larger latency, but landline-based international phone calls work, and they're all carried on this fiber. And the final one is the one we think about all the time, which actually not too many people really understand, and that's Moore's law. Moore stated this law in 1965, and what he said was not that computers would be faster, which they have become, and not that they would draw more power, which they do, but simply, he said that, I think I can put twice as many transistors on a given area of silicon every 24 months for the foreseeable future. Actually, he said for the next few years. And the next few years is, of course, turned into half a century, and we're still writing that. So before plunging into the examples, let's do a little review. This is, I promise you, the only slide that has any math on it whatsoever. The equation at the top line is the thing that actually dominates people who think about computer architecture. The power and the power of a single inverter on a silicon chip with a given capacitive load at a given operating voltage and a given frequency is given by that equation, CV squared F. Notice the square. That's a very interesting thing. Now, if we scale down the dimensions in every way linearly, that is, shrink the length, shrink the width, shrink the thicknesses of everything, then we get a new number for the power. It's CV squared F prime, the new frequency, divided by K cubed, where K is the scaling factor. That is how much you shrunk it. Going from a 90 nanometer process to a 45 nanometer process is a scale factor of 2. So this is an interesting observation because it means that you have a new chip. If you have a new chip running in the same frequency regime as the old chip, it will be 1 over K squared the size, which is related to the cost. So it'll be K squared as expensive. 1 over K squared is expensive. And it'll dissipate 1 over K cubed the power, which means it'll run 8 times the battery life for a factor of 2 in K. That might be a pretty good deal, but unfortunately, that is not the way the semiconductor industry has chosen to apply Moore's law. And the other thing you have to understand is that if you scale the frequency up, then the power per unit area on the chip, which is the thing that tells you how much heat you have to remove from it, is unchanged. And since you're going to put more stuff on the chip, power is going to go up. So how has this been used? In 2 ways, basically. One is that memory manufacturers used it to scale up the density. So that was that factor of 48,000. They run it at a lower voltage, slightly higher frequency, and a little more power, but they get a lot more bits. The CPU manufacturers did something else. They said, go to higher clock rate and go to more complex designs, and therefore bigger designs, in order to make sequential programs run faster. And the result was the power wall and the memory wall. So I think that a future trend that we're going to see in CPUs, and we're beginning to see it today, is that we're going to see not just a small number of cores on a chip, but we'll see a lot of simpler cores, or perhaps a few simpler cores and a few large cores. And more likely, we'll see the thing that Craig alluded to, which is a system on a chip, which has virtually everything, including the GPUs and the I/O. And we'll be able to do this because Moore's law keeps grundling along. We're now at about 28 nanometers and shrinking, and it's still holding up. But this is all going to have a pretty profound effect on the software. So let's go now to the examples that I chose. The first one is virtual memory, something that we believe we must have in every machine on the planet, almost. This was a technique that was invented for the Manchester Atlas in the 1960s, and they had a problem. They had a 16 kiloword core memory, small and for the time pretty fast, and a 1 megaword magnetic drum memory. Just for calibration, how many of you have programmed a computer where the primary memory was a drum? 1, 2, 3, 4. Okay, well that's pretty good. It appears that we're doing a good job of care for the aged. So the Atlas idea was very simple. Make the core memory appear to be as large as the drum. And the way they did it was they divided up the core into 32 512-word pages. That 512, by the way, is with us today. And they used an associative structure called which we would now call a TLB, to map the virtual drum addresses to real core addresses. So this is just another one of those examples in computing where any problem can be solved by another level of indirection. And they also had a learning program, which we would call a scheduler or a swapper, to decide when to transfer pages back to the drum. That is, when they were dirty, had been written, and they became unneeded anymore. This technique is used in essentially all computers on the planet today, except for supercomputers and embedded systems. The supercomputers will not put up with the overhead of virtual memory. Seymour Cray is reputed to have said, real computers need real memory. And of course, embedded systems don't do it yet. They don't use it yet because they care about predictability. And VM does introduce a lot of sort of noise into the predictability of your system in terms of performance. So unfortunately, these good ideas often get messed with as technology changes. And the memories grew faster than the page size. That meant you needed larger tables. And everybody knew then, and still knows today, that associative memories are very expensive and slow. So that means you have to cache the page table. That's where we got today's TLB. And of course, we're clever people. We're not very good at remembering things, but we're clever people. And so we went to more complex data structures. And sometimes we got into anticipated problems. When I was working on that tablet PC a decade ago, we noticed one thing, which was it came out of standby just as fast as it came out of hibernation. And it ought to be a lot faster, because in hibernation you wrote everything to the disk, and then you had to spin up the disk when you came out of it. Standby just turns everything off except the memory and the state necessary to start the machine up quickly is supposed to be there. And we looked around for a while and finally figured out what the problem was. The problem was, if you had been using, say, your video driver for a long time, the code that it needed when it started up was no longer in memory. Now, the video driver manufacturers knew about this, we knew about it, and so Windows arranged to send a message to all the I/O drivers saying, please get yourself ready to go to sleep. And unfortunately, the video driver people were not very good at developing software, so they realized that they could just say, did it, thank you, and do absolutely nothing. That means, of course, that when you turn the power on, what happens is you've got to spin up the disk because it's paging in stuff because it hasn't used it for a long time. So what I told people for a couple of years until we finally shook people by the neck and said, stop doing this, is turn off paging. It'll work fine. Your system will eventually run out of virtual memory after a few days, and you'll have to reboot it. After all, the boot button is the garbage collector of last resort. And that worked great. 1 second startup. We've mostly fixed that today. So problems that VM still solve today are these: protection, relocation, fragmentation, and all of them have software-based solutions. Can we do it? Can we get away with without a virtual memory system? It does klutz things up quite a bit. And TLB shoot down in a multiprocessor is a terrible problem. The thing to notice here is that the size of real memory for the kinds of applications that most people run, not the supercomputer guys, is no longer a problem. So we invented this technique in a time of scarcity. Is it still a good idea? I don't know, but I think it's worth asking the question. Example 2 is coherent memory. We expect a certain right ordering. We may not know quite what it is, but we expect something that's sort of rational. Sequential consistency would be the right thing to ask for. But for a long time, this wasn't an issue. If a processor did a write and then it did a read, it was sure to get the value that it wrote. And since we didn't have multiprocessors, it wasn't an issue. And the only thing like a multiprocessor that we had was I/O. And caches made things a little bit different, and multiprocessors made them a lot different. So for the early multiprocessors, we used what were called snooping protocols. Every processor could see every write that was reflected on the backplane bus. And that was fine. The protocols were easy to build. They worked well. We could build 6 processor machines. We had multiprocessors in our lab in DEC in the early 80s, I'm sorry. And they worked just fine. But as things got more complicated, as they always do, we had to do something different because buses no longer work. You have to have point-to-point electrical links in order to send signals at high speeds. And so the protocol complexity just went through the roof. And today, for instance, one of the largest users of model checking for correctness verification is actually Intel. Every time they make a new protocol, they verify it and they prove it correct. They learned their lesson with floating point. So I've thought about this one a lot because I invented some of the early coherence protocols, and now I think that was a kind of a bad choice. Why did we do it? Well, we knew at the time from a paper in 1977 that coherent memory and message passing are duals of one another. That is, under a certain change in the way you look at things, they will do the same thing. And yet we chose memory coherence. Why? Given that messages are actually quite a bit simpler to implement. And one possibility is that programming is easier. And I think that's true, because if you write an incorrect multiprocessor program, you can debug it into existence almost. You can never get it quite right, perhaps, and it will still give you the wrong answer, but if the occasion on which it does so is rare enough, it might not matter. But the other possibility is that we didn't look forward into the future carefully enough. And we didn't see how hard it would be to scale these things up. And so would we make the same choice today? I'm not sure. I mean, one of the things that we see are increasingly experimental operating systems, to the extent that there are any such in the world anymore, are looking at the question of, can I build systems based on message passing rather than on coherent memory? Just because it's so hard to do. So example 3 is threads and locks. And this is an area that is a little strange because there's a good quote here. Can you all read it? I think you can, from Edgar Dijkstra in 1968. And what he was talking about was a multi-programming system on a single processor machine, the THE multiprocessing system. And I suspect that when Edgar said moderates, the best people, what he really meant was Edgar Dijkstra. So, but I thought it was interesting that he saw the problem. And the difficulty is that lock-based programming is hard. And what people used to do is just use coarse-grained locking, which is easy to get right, but it doesn't perform very well. So you go to finer and finer grained locking, and what happens is the program gets harder and harder to reason about. And in fact, programming with threads and locks is actually still kind of an art. And I think one of the best examples and sort of prescriptions for how to do it was written by a colleague about 6 years ago. It's an MSR Tech report. It's called Programming with C# Threads and Locks, I believe, by Andrew Birrell. This tells you how to do it right, but apparently nobody has read it. So, the real problem, and I didn't realize this until a few years ago, was that lock-based programs don't compose. And since we're very big on composing abstractions to build bigger abstractions, that is a fatal failure. It's not an educational problem, which I thought it was. I figured if we just were better at teaching the kids how to use this stuff, they'd get it right. But I don't think it's true. So we're in this soup because we're going to get big coherent, non-coherent memory systems, and we're going to get a lot more CPUs, and we're stuck. Because we can't just have the best people. Some people say, employ the best people writing libraries, but that only goes so far. So what are some alternatives? Well, one of the things that's been studied intensely over the last decade is called transactional memory. So transactional memory is an attempt to get the ACI properties out of the ACID properties of databases: atomicity, consistency, independence, and durability. You can't get durability because this stuff is actually in a dynamic RAM, but you can get AC and I. So people have done a lot of designs, mostly for software-based transactional memory. Unfortunately, programmers are very conservative. They won't use something if it's slower than what they use now. This delayed the introduction of garbage collection as a well-used technique for over 20 years. And of course, transactional memory has problems of its own, like I/O. You can't do any in a transaction because you can't undo it. You can't unfire the missiles. The same kind of coarse versus fine-grained arguments that apply to locks and threads apply to transactions. You've got to be careful. The thing that I don't like about them, but I'm coming to dislike less, is transactions are actually speculation. And that means that if it turns out that your transaction cannot commit because it conflicts with something that somebody else did who did commit, then you've got to abort, throwing away a lot of work that you already did. This is a bad thing because it wastes energy. And right now, you would not want to think about our power bill for the data centers. It's a lot of money. So the problem is we don't have any reasonable implementations of transactional memory, and we need some. We need some benchmarks, and we need to build a few real systems to get an idea of whether the abstraction is valuable. And we're actually starting to get this kind of experience in our lab down south. We have what is perhaps the only fully hardware-based transactional memory system on the planet. It runs on a 13-core experimental processor that we built called Beehive, which is slow. But it is a multi-core, and it does allow for a lot of experimentation. And the way we did it, we get an additional benefit, which is memory coherence, but only where you need it. You only get coherent behavior from your transactional variables. And so you don't pay for it if you don't need it. So another thing we might do is go back to message passing. And all of these mechanisms are there to solve one problem, the problem of access to shared mutable state. And message passing is, in some way, the cleanest answer, because what it does is it legislates the problem out of existence. There is no shared mutable state because there's no shared state. All things that have to be shared are shared by sending explicit messages to a recipient. And usually this is implemented on top of coherent memory, but it's funny, the way the implementations all work is, first you build a very efficient message passing layer in the hardware, and then you layer on top of that the abstraction of shared memory. And then you layer on top of that message passing. There's something wrong with this picture. So that takes us to example 4, and we better hustle right along. Complex CPUs. And for this one I need a bit of a timeline, because you have to kind of remember what went on in computer architecture for more than a half a century. The 50s and 60s were very interesting. Very few of us were alive at that time. Only those guys who raised their hands to the earlier questions. But this was really the golden age of experimentation in computer architecture. We saw computers that were optimized for processing decimal, processing strings, written for a single language like the Burroughs B5000, which implemented ALGOL, more or less on the hardware. Machines to execute Lisp directly, and stack machines. We built a couple of those in our lab at Park. Alto was not a stack machine, but it was used to implement a stack machine. So by the 70s and 80s, this had mostly settled out into two camps, which started fighting. As when you're down to two, you'd like to get rid of the number one guy if you're number two. And this was the era of RISC-CISC warfare. And the RISCs, which were typified by machines from IBM, Stanford, and Berkeley, were pitted against the CISCs, the complex instruction set computers, of which the major purveyor was Intel. And everybody wrote papers of the form, mine is better and bigger than yours. And that gradually died out, because as each camp read the other guy's papers in order to figure out what to write in their paper, in a more inflammatory paper, they discovered, hey, you know, those guys, some of them have pretty good ideas. And it was like two warring nations that finally decided to make peace, and then they all began intermarrying. Everybody did pretty much the same thing, and today if you look at a RISC versus a CISC, there's not much difference. So what might happen? Excuse me one moment. Yeah. So, more on complex CPUs. In the 90s, we switched. We switched from actually building new architectures to elaboration. And people began to look for increasingly complex mechanisms in order to exploit the last little bit of instruction-level parallelism in their programs. We got multi-level cache hierarchies, we got multi-threading, we got speculation everywhere. And all of these things represented incremental advances in performance at the cost of lots of complexity and lots of power. This is the complexity wall. Today, you buy a CPU chip, and 80% of it does not actually go into executing the instructions. It goes into making some facet of the instruction execution a little bit faster. And the problem is that most sequential programs don't exhibit very much ILP, perhaps 3 or 4. And so we spend all this treasure, actual treasure, in order to exploit something which gives you a factor of 4. That doesn't make too much sense to me. So possible directions that the manufacturers are looking at are things like these. The Intel single chip cloud computer, which is lots of simple cores, no coherence, very efficient on-chip message passing, and a very efficient inter-core network for doing it. Is this going to be the wave of the future? I'm not sure. Intel doesn't make any claims at this point, But there are an awful lot of people out there who have prototypes of these things that are using them in very interesting ways. We have some in MSR. And another possibility, if you remember back on that first slide, we talked about the 1 over k cubed thing, where the processor should be 1 over k cubed the power and 1 over k squared the cost. Well, some people are beginning to ask that question, and they're saying, you know, maybe my computer is fast enough. Maybe I don't have to buy the next greatest thing. And this strikes fear and terror into the hearts of a lot of people who make chips, because that's a bad thing. You want to supply more silicon. Their goal is to turn every beach into surplus chips. So, but the fact of the matter is, I don't need 100 watts to edit this presentation. In fact, I do perfectly well with this gizmo, which gets 13 hours of battery life. I can get across the Atlantic, all the way to California, on one battery charge. So, fifth example, interrupts. You might think that interrupts are sort of a fundamental axiomatic property of computer architecture. They're not. They were put in to solve a particular problem. And that problem was, what happens when I/O completes? And how do I keep this very expensive computer doing something at all times? And when computers were very expensive, this was a reasonable thing to do, although it does klutz things up a lot in terms of the complexity of the hardware, and in fact also the operating system. I mean, how many of you have worked down at the bottom of Windows and worried about interrupt delivery and how to set up the apex in order to make it happen in the way you want it to? Not too many. It's a very highly specialized job. Not too many people can do it, and fewer than those can actually get it right. It's possible to build systems without interrupts. And it was done, for instance, in this thing called the Pluribus in 1972, which was the ARPANET IMP version 2. The thing we would now call a router. And it's a very nice way to do business, because your software is reasonably predictable. You use non-preemptive multitasking. And if your processor doesn't have anything to do, it just waits. Now, that was a big deal when the processor filled a room and cost millions of dollars. Today, cores cost a nickel. And there are a lot of them. So is it really important to have all this complexity? I don't know, but I think that's one of the things that I would leave out. And in fact, in this Beehive machine that we did in our lab, we did leave it out. And so far, we haven't felt very badly about having done that. Of course, we haven't tried to run Windows either. The final example is one that's going to probably cause the tomatoes to come down towards the stage. This was something that Craig alluded to, and he said I probably wouldn't talk about it, but I'm going to do it. The sixth example that I think we ought to be rethinking, and we are in fact, is packet-switched networks. And I wouldn't advocate this for the internet as a whole. I did that 20 years ago, and I got a bit of a black eye from the internet community. The thing worked, but they didn't want to hear it. It was contrary to the religion of the day, which is still the religion of the day, by the way. But things change, and technology marches on, and it is the 21st century. And so today we have a new opportunity to look at packet switch networking and examine it carefully in light of the realities of our data centers today. And if we look at them, they are not the internet. They're nothing like it. They have a known topology with known names and small diameter. You can do things if you have a small diameter network that you can never do in a network the size of the internet. Fewer end nodes. Tens of thousands versus hundreds of millions. And faster links. Today, inside our data center, we top out at about 10 gigabits, but 40 and 100 is coming very soon, along with the progress in those glass fibers and the ability to drive them. So, we also have a very different traffic patterns inside the data center than we have in the internet. So why did we start using packet switching? Well, in the early days, it was adequate. In our lab, we had a packet switch network called Ethernet, which ran at 3 megabits per second. And that was fast enough, even for voice. We had a system that was very much like today's VoIP in 1975, and it just ran on the Ethernet along with everybody's data traffic, and it worked just fine. Of course, we didn't have the same traffic loads we do today, but the nice thing about it was that we could multiplex traffic onto those very expensive links. And because the diameters of the network was small, retransmission on loss worked pretty well. And we didn't have a problem with short addresses. The original Ethernet had 8-bit addresses, which we thought was quite enough. Of course, that's always the error. Not providing enough address bits is the biggest error that an architect can make. And they all make it at one time or another in their career. I've made it about twice. So moving right along, things got faster and the links got more reliable, but that brought some problems. I said earlier we had to move to point-to-point links for everything. Well, this is one place we had to do it. Point-to-point links rarely make errors, but you still need a lot of buffering in a switch or a router, not so much for errors, but to handle the problems of congestion. And in those switches and routers, you make a lot of decisions at each switch along the path based on looking at the packets in order to decide how to route them. So when you buy a switch from the major network providers, what you're buying is a huge amount of static RAM buffer memory, a small switch in the middle, and thousands of tiny processors to process the packet headers. A lot of that you can get rid of. This is going to be a real problem when we move up the link speeds because there's less and less time to look at the headers. And of course, IP, which is the thing I would like to root out, has a serious problem because its fundamental mechanism, which worked well in the early days but no longer works well today, is that the sources they equate loss with congestion, which is not correct. They didn't have any better way back in the 70s, but today we do. And so if you have a Windows-based flow control protocol, it doesn't work well if you've got thousands and thousands of packets in flight in the network, which we do today. And sources, of course, get the information about the damage long after the damage was done. So I'm arguing today that we ought to revisit circuit switching. And of course, circuit switching is used in the internet. It's used in the backbone. The principal ISPs, the backbone ISPs, establish ATM links, circuit switch links between themselves, and they stay set up for a long time. And that works because they can multiplex data onto those links and use statistical multiplexing to aggregate. These networks use admission control rather than congestion control. So if you can't get a clear call to your destination, you get a busy signal. This is very much like a telephone network, and of course that's what it's patterned after. The problem with a thing like this, and the key thing you have to worry about, is to make the call setup time much, much less than the transmission time. But if you can set up a call very rapidly, send your data, and then tear it down efficiently, you might do a good job. And the nice thing about this is that this works pretty well if the number of hops is small and the links are relatively short. The nice thing about it is the switches are much, much less complicated. I mean much, much less complicated. And they require almost no buffering. And so we're looking at this, a 128-port switch for our data center networks. And the curious thing is that we can build them not with custom silicon, which is what most people use, but with field programmable gate arrays. They're not as inexpensive as they would be if you implemented them with custom silicon, but it's possible in FPGAs, which was somewhat surprising to me. So that's most of what I have to say. I'd like to give you some final thoughts. because I can't resist in a talk like this making a few grand challenge kinds of things. So we're going to do things differently in this new century. It's not quite so new anymore. And I think we should rethink some of the decisions we made last 50 years based on what's changed, and what things are like today, not what they were like when the mechanisms were invented. And one of the things that I think, and Craig talked to this quite a bit in his talk, there are still a lot of things that computers can't do. Some of the things that they can't do will have to wait for quantum computing. That's probably true. But they can still do a lot of things today that we would have thought of 50 years ago or 40 years ago as approximately equal to magic. And we have a long way to go with roughly the kind of machines that we have today, given some of the kinds of changes that I talked about earlier in the talk. And what I'd like to see is computers that can do some of these things, like drive my car. This talk is almost a year old now, and I believe that that challenge has now been passed. A computer or a set of computers can probably drive my car better than I can, because the cars that you see driven by computers don't have the same kind of dents in them that my car has. So there must be something going on. And it's not that they have a better body shop. Right, the new user interface thing speaks to the second thing. I want a computer that's a colleague. I want it to know about me. I want it to know roughly my dislikes and likes and what I'm liable to be doing when I sit down and start doing something at it, and I want it to help me. I don't want it to be Clippy. I don't want it to be in my face. How many remember Clippy? I said we were a forgetful field. I have evidence to support this business about forgetful field. If you read papers and you look back through the bibliography at the end of the paper and ask, when was the oldest citation? These days, you see 5 years. If it didn't happen within the last 5 years, it just simply didn't happen. And that's often not true. I mean, other fields don't work like that, but we do. So I'd like also to help educate my children. I worked on that a little bit with Craig. It's very, very hard. I would like to have computers that enhance my privacy rather than eroding it. I'm very skeptical about social networking. Part of that is the fact that I'm old, and part of the fact that what I see is people giving away a lot of things that I think they may come to regret in the future. We're beginning to see a little bit of this in people asking, how can I get some of the things that I put on Facebook off, so that when people troll over Facebook for an employment reference, they don't get some of these things that I'd rather not have them see. So I think we've got a lot of things to do, a lot of things we can do with the tools that we have or are rapidly developing, and we'll have to develop a lot of new tools. And I actually envy you guys, because you have the job of doing this. I'm old, I'll be out of here in a few years. But I think it's going to be just as exciting and vibrant a field today as it was when I got into it 40 years ago. So thanks very much. So we have a few minutes for questions, but not very many. Right there.
You mentioned FPGAs being more expensive than custom silicon. What about what factor?
Well, the thing that's expensive about custom silicon is not the individual chips. They're essentially free. It's the design, and that runs $25 million as sort of an ante of entry. Mass costs today to fab a competitive chip are just astronomical. Far back. Microphone, number one.
Thank you. What do you think about using GPUs for accelerating computation?
I think that GPUs are great. I mean, they're certainly much better than the Swiss Army knife CPU that sits alongside them. I mean, you have to realize that today's general purpose CPU was not optimized to any given task. It was optimized to do a lot of things reasonably well, and it does that. A GPU is highly optimized to do one thing, and boy, it does it superlatively. So if you can get your problem to fit into a GPU, or if you can morph the GPU into a GPU that you can actually apply against your problem, it'll do a lot better.
Hi, Chuck. You mentioned about CIS versus RISC. I was wondering your perspective on VLIW or Itanium, that style of computing.
Itanic. Yeah, well, that's one of those things that kind of died out, except it was kept alive, I think, on life support for a lot longer than the reality justified. I mean, VLIWs were, of course, big in the late 80s and early 90s, and everybody thought, oh boy, by going to VLIW, we will be able to get that ILP that we couldn't get with these simpler techniques. Well, I'm sorry, it just wasn't there. And so, you know, they were just, they had more cash to keep it alive.
What do you think about the penetration of FPGAs in the consumer devices, like phones, cameras?
A lot of people are using FPGAs in consumer devices but not very big ones, because the big ones are expensive. I think it's possible that reconfigurable stuff will move on to the SoCs that we'll see, but in those cases, it's not clear that they'll really have much advantage. I mean, FPGAs are good for about three things. There are certain algorithms that they can make run really fast, mostly having to do with signal processing. They're good for experimentation because you can build big systems with them. They won't run real fast, but you can build them and check things out. And they're good for glue logic, the simple stuff that connects up a lot of other things, but that's less and less a demand as everything moves into one chip. So I'm not too optimistic about that. I think they'll have their place in the world, but it won't be in a phone. We seem to be...
Chuck, interesting discussion. I would like your thoughts on SoCs in particular. In the early 90s, IBM tried to do an SoC with the 486 for the consumer market, and we failed miserably because when you try to integrate fast-moving technology into an SoC, you have an inherent latency to deliver that SoC to the market, and you can build an ASIC-based system much quicker and take it to market. So given that...
Right, but ASICs are based on standard objects, right?
Sure.
They just happen to be small standard objects. SoCs can be based on standard objects, it's just that they're a lot larger.
That's right, but because you want to put mature technology in your SoC because of the cost, you tend to have less fast-moving technology in an SoC than what you could build in a discrete system.
And this is exactly what Intel found when they built the single-chip cloud.
Right.
Those are old cores.
Right.
There's nothing really hyper wonderful in that chip from an architectural standpoint.
So given that dynamic, how would you see SoCs play out if the processors become sort of flatline in performance because of Moore's law and investment flows into the supporting technology such as networking and storage and compression, et cetera?
Well, my own belief is that when the CPUs kind of flatten out, they will not be fast-moving technology anymore.
No,
so,
the CPUs won't, but the auxiliary technology will see investment because you showed the chart that suggested networks are only a few times faster than in the past few years. Disks, you didn't show disk latencies, but it's probably the worst of the
That's the worst,
situation,
yeah, that's really
right?
bad.
So you're replacing that with flash, but those technologies will see much more aggressive investment because the CPU won't be the reason you buy a new system. So
Right.
it seems to me SoCs will be lagging those fast-moving technologies in how you take it to market.
It's possible that's true, but I think there are a lot of ways to play the game. You can make the tools for assembling an SoC a lot better than the tools for assembling an ASIC. You could work in that area and get some of that back. But you may be absolutely right. SoCs may not work out well. I think, but it's definitely not tested yet.
Thanks.
Anybody else?
Hi, Chuck. Does the rise of SSDs as part of the memory hierarchy change your questioning of virtual memory? Does it factor in there somehow?
I'm actually quite worried about SSDs because the problem with SSDs is that they have, unless you're very, very careful with them or you use them in very careful ways, they have very serious lifetime problems. And I'm quite worried that people are rushing headlong into something where they're going to run up against a brick wall. And that brick wall is the lifetime of the device. I mean, I have argued that, for instance, for critical data applications, you should never use MLC flash memory. Never, ever, ever. Because although it's twice as cheap as single-level cell, it's only 1/10 the reliability. And so in our quest to build sort of zero-cost data centers, we're possibly making a mistake. And I think we should look very carefully at that technology. I mean, everybody has the next great thing in non-volatile storage. I mean, we've heard a lot about phase change memory and other bits of science fiction, memristors and the like. But these things really take a long time to get developed and get the kind of investment that makes them reliable. I mean, disks didn't used to be reliable. Anybody else? Okay, well, thank you very much.